Hello, I'm Avian Kurdiasa, and I'm presenting with Noah Greer. This presentation covers our final results on the experimental validation of flow through a TPMS gyroid lattice following the project update we delivered last Friday. Today we will focus on the 9 test cases we conducted and the resulting comparisons against published flow regime predictions.
A brief recap of the experimental setup for context. The flow loop consists of a circulation pump, damping tanks on the inlet and outlet sides to attenuate pump pulsation, and a test section housing the specimen. The specimen is a clear resin SLA printed gyroid core made up of a 80 by 80 by 160 millimeter sample that has been clear coated on all internal surfaces for optical access and bonded into an acrylic flow chamber using UV cure resin. Rhodamine B dye is injected upstream of the gyroid, and the flow field is recorded with the camera positioned normal to the specimen. And by varying the volumetric flow rate, we sweep Reynolds number across the regimes of interest and characterize the flow behavior through direct visualization.
So this is our test sweep, which consists of 9 cases spanning Reynolds numbers from 460 down to 38. The predicted behavior column references work by Kus and others and Bora and others, which serves as our baseline for the expected flow regime at each Reynolds number in a gyroid lattice. Kus places a single turbulent cutoff at Reynolds 300, where above 300 is fully turbulent. Below 300 is classified as transitional or laminar without further resolution. Bora defines a band from Reynolds 70 to 210, where a transition from laminar to turbulent could take place. And we'll proceed through each case from highest to lowest number, a Reynolds number, and compare our observations against these predictions and identify the observed regime boundaries.
Case 1, Reynolds 460, was predicted turbulent, and we observed significant mixing within the first unit cell, large velocity fluctuations, pronounced tumbling, and a fully mixed outlet. And this is consistent with the predictions from the papers.
Case 2, Reynolds 407. This was also predicted turbulent. The observed behavior is very similar to RE 460, fully developed turbulent mixing throughout the lattice with no visible coherent structures, which is consistent with the predictions.
This is case 3. It's a Reynolds number of 353, and it was also predicted turbulent. And we observed a slight decrease in the mixing intensity compared to the higher Reynolds cases, but the flow still remains heavily mixing and tumbling throughout the specimen, and it is still clearly turbulent flow.
Case 4, Reynolds 289. This one is interesting because it's a changeover point. It's slightly below the claimed fully turbulent value that Kus claims at 300 and is above the number that Bora claims at 210. In this clip, mixing intensity was further reduced, but the flow remained fully mixing with no preserved coherent structures and is consistent with Bora's prediction.
Case 5, Reynolds number of 249, predicted transitional by Kus and turbulent by Bora. And we observed the first signs of coherent structures holding together through the specimen, indicating that the flow is beginning to depart from the fully turbulent regime. And the flow was not entirely mixing, but it was still largely mixing. And we classified this case as turbulent, but at the lower end of the turbulent regime. This case is also similar to the previous case at Reynolds number 289, where it is between where the 2 papers disagree on where the turbulent Reynolds number is.
Case 6, Reynolds 205. This is predicted transitional. Mixing intensity has decreased relative to higher Reynolds cases, but the eddies characteristic of turbulent flow remain clearly visible, particularly in the right video. We classify this case as turbulent. This is the second case in which our observations place the flow in a more chaotic regime than the Kus prediction indicates.
Case 7, Reynolds number of 157 and predicted transitional. And this is the first case that we classify as transitional. Mixing is noticeably reduced, intermittent unsteadiness is visible, and coherent structure is partially preserved through the lattice. The intermittent character matches the defining feature of the transitional regime, and our observation agrees with the Vorer prediction here.
Case 8, Reynolds 103, predicted transitional. The flow is close to the laminar boundary, but retains residual unsteadiness, and the dye has not yet settled into clean, streamlined behavior. We classify this as transitional. Vorer predicts on the lower level of transitional to laminar, so this agrees with the study's findings.
Case 9, Reynolds number 38, predicted laminar. This flow was cleanly laminar. The dye enters the chamber as a coherent plume and follows the gyroid channel geometry with little to no breakup or eddy shedding. And our observation is consistent with the Vorer prediction.
So I'll summarize the full data set against the two references. Cases 1 through 3 from Reynolds 460 down to 353 were observed as turbulent. Both Koos and Vorer predict turbulent behavior in this range, and our observations agree with both. Case 4 at Reynolds 289 was observed as turbulent. This is the first case where the two references disagree. RE 289 sits above Vorer's turbulent threshold of 210, but below Koos's cutoff of 300. Our observation agrees with Vorer. Cases 5 and 6 at Reynolds 249 and 205 were also observed as turbulent. Both values fall below Koos's cutoff, placing them in the transitional or laminar category per Koos. RE 249 sits above Vorer's transitional band, consistent with turbulent. RE 205 sits essentially on the Vorer upper bound of 210, and our observations at these two cases agree with Vorer and disagree with Koos. Case 7 at Reynolds 157 was observed as transitional, which falls squarely within the Vorer transitional range and is consistent with the Koos non-turbulent classification. Case 8 at Reynolds 103 was observed as transitional. This is within the Vorer transitional range and is consistent with Koos. Case 9 at Reynolds 38 was cleanly laminar, and this sits below the Vorer lower bound of 70 and is consistent with Koos.
Our main finding is that our observed flow regime boundaries align well with the Vorer predictions across the entire Reynolds sweep. The upper boundary of turbulent behavior in our data falls between Reynolds 205 and 157, which matches the Vorer transitional upper bound of 210. The lower bound of transitional behavior falls between Reynolds 103 and 38, which matches the Vorer lower bound of 70. Our observations are also consistent with Koos in the fully turbulent cases above Reynolds 353 and in the laminar case at Reynolds number 38. However, between Reynolds 289 and 205, Koos's single turbulent cutoff at 300 does not match what we observed. We saw fully developed turbulent behavior at Reynolds values where Koos would predict non-turbulent flow. Reflecting on the experiment, there are a few areas where tighter control could strengthen the analysis and help resolve the disagreement with Koos. Dye injection was not precisely controlled for flow rate or density, and refining that would reduce uncertainty at lower Reynolds numbers where injection momentum matters most relative to the bulk flow. Geometry also plays a role. Unit cell size, wall thickness, and relative density all influence transition behavior, and characterizing how our lattice parameters compare to those used by Koos and Vorer would clarify how much of the observed difference is geometric or experimental. And both of these are straightforward to address, and they point directly toward the next phase of work.